Okay. Started. Okay. So good morning or afternoon for everyone. So today I'm going to speak a little bit about an application of resolution of singularities, which is the uniformization theorem for Q sets and for sub-quasianalytic sets. So just want to recall what we did last course, which is the theorem that we're going to use today. So last course we just stated, so we gave all of the necessary definitions and discussed a little bit about the hypothesis to state the theorem of resolution of singularities. So in particular, which is this theorem here. So we fixed it. So I repeated here the statement that we saw last time. So we consider a quasianalytic class, M a quasianalytic manifolds, a simple normal crossing divisor, and a privileged ideal sheaf. So in particular, we discussed a lot the word privileged the last time. And then we said that for every relatively compact open set, we gave an example just to show that it cannot be read globally, in general, by a finite number of lines up. But in any case, for every relatively compact open set, we are able to find a resolution of singularity. That is, we restrict everything to this open set. And then there exists a finite sequence of blinds up, like this one, where the sigma i's are all compatible with the previous exceptional divisor, and the pullback of the ideal by all of the composition of the blinds up is now monomial, which was our objective after all. So this was the result, and the result that we're going to use today. Then afterwards, we recall the definition of what proper is. So proper means that for every compact set of M, even when I'm preparing, I sometimes make mistakes. Even when I have time, the preimage of the compact set is compact. And we talked about phi being semi-proper. That is, we said that for every compact set of M, there would exist, so this is actually a semi-proper covering, as we're going to see. There exists an L such that the phi L is equal to K. And then we provided a lemma that missed an important point. It was like in the end of the course, and I wanted to finish with the proof of this result. And I forgot to add a very important point so that the lemma is not empty. And the lemma says that if we take a semi-proper Q morphism, quasianalytic morphism, then there exists a generically local isomorphism, which is a Q morphism, Q of n tilde to n, such that the composition is proper. And of course, we want the image of n tilde to be equal to the image of n. So in the previous version, we did not add this property, and then you could always take n tilde equals to a point, and tau being just the immersion of a point into n, and the final morphism would be proper. But of course, we want to be some sort of covering in some sense, right? And the idea of the proof was simply to consider the local models, the projection of the sphere into Rn, and this you would use to cover compact set L that would be sent to complex sets K, where this K, you would take it some K alpha, where the K alpha would be locally finite, a local finite covering by complex sets of your manifold M that is in here. So that's what was the idea of the lemma. And today I want to do a second lemma, a very short one, and before stating the main result of today, and the main result that we're going to actually talk about the proof, which is the uniformization theorem. And we're going to start with the uniformization theorem, which is a parameterization theorem for sets. Okay, so this was kind of the recalling of last time. So just what is the lemma that we want to say here? It's a very simple lemma. It's we take a connected open set of Rn, and we take a function defined over this open set, which is non-identically zero. Then the set of non-zero points of this you take U minus Z of F, is open and dense in U, is actually something, we can actually show that it's actually something of Hausdorff dimension is smaller, strictly smaller or equal than n minus 1. It would follow by the same proof. And the proof is quite simple. It's just a consequence of long-range preparation theorem. So let A be a point in C of F, which I recall these are the points, let's call it X in U, such that F of X is equal to 0. And since f is not trivial 0, we will say that we know that the Taylor expansion at A is not 0. Well, here I don't need equivalent. It's not 0 by quasianalyticity. Otherwise, the axiom would tell us that f would be equivalent to 0. So apart from the interchange of coordinates, we may apply Lagrange preparation. And with the Lagrange preparation theorem, it just becomes evident that this is the case. That that is open is trivial because it's just going to be the preimage of the set of non-zero values of f, so it's open. But the fact that it's dense is going to come from the Lagrange preparation. We know that's going to be as a polynomial given f is going to be written locally as a polynomial with coefficients that are sensitive function. So even better than just open dense, we know that z of f has a Hausdorff dimension smaller or equal to d minus 1. And in particular, note that I didn't talk too much yet about the dimension of a quasi-analytic set. So a set given by the zeros, for example, of f. One could attach the Hausdorff dimension to it, but there is another way which is compatible with the Hausdorff dimension, which is more explicit, and it's going to be via the next theorem, which is a parametrization of these sets, a good parametrization of these sets. So the main theorem of today, in the first version of it, at least, is going to be the following. So let X be a closed Q set. There exists a proper generically immersive Q-morphism P of n to m such that P of n is equal to x. And when m here is the ambient variety as usual. So this is the result that I want to prove in the next 10 to 15 more, even 20 minutes. And it's the result that I want to prove in a way that is sufficiently, which is complete, right? So the first idea here is that by using the first of these lemmas, the result becomes local. So we just need to prove the existence of phi, which is not necessarily proper, but just semi-proper. So by lemma 1, it is enough to show the existence of a semi-proper morphism. Satisfying the other conditions. Now that we have this, we actually have a local problem, because now we can just compose it with local immersions of sufficiently small open sets, cover the entire manifold by some covering by open sets, some locally finite covering by open sets, and then argue for each one of them of the existence of this phi. So now the problem, so we may now argue locally. And in particular, since we can restrict to open sets, we can actually suppose So we may suppose two things. First, that X is given, there exists a privileged ideal I such that V of I is equal to X. So that's the first thing, because we recall that for every Q set locally, we did have a privileged ideal I, actually even, as we're going to see, finite type ideal I, such that the zero locus is going to be equal to X, but for now just privileged. And the second thing, there exists a resolution of singularities MR, ER, sigma R, not necessary. M1, E1, M0, E0, and in this case here, we can even take it equal to M, because we are able to argue locally, so we can always suppose that M is just local, an open set, it's a very small open set. And here we are going to take, in our case, we didn't start with any exceptional divisor, so we can take it empty. The E0 would be empty. Just a little comment. In the theorem, we had to take some relatively compact open set, and then there is the existence. But of course, since the result is now local, it's enough to take some local covering. We can take a local covering by relatively compact open sets of M, and then argue in each one of them. So we can assume, as written here, there exists a global resolution of singularity with this M equals to the empty set, with this M equal to M0 and E0 equal to the empty set. Now, although the result that we want to use in the end is going to be in terms of M and the empty set here, we're actually going to prove the result as an induction, so it's going to be convenient to do it via E02, just a simple normal crossing divisor that we start with. Okay, so I'm actually not going to use in the proof that we start with something that where the exceptional divisor is empty. Okay. And now the idea of the proof is going to be an induction. So in particular, let me just note this, which is important. The pre-image via the entire blow-up sequence of X is going to be contained in the end in ER. And the reason for this is simply because the ideal sheaf, the end-up ideal sheaf, is going to be, after all of these blowing ups, are going to be a principal ideal, which is monomial over the exceptional divisor. So local is going to be just given by the product of terms of the exceptional divisor. So the zero set of the total transform of I, this guy here, is going to have zero locus inside of VR. So this is the first remark that we make, that the pre-image of X is contained in the exceptional divisor, the last one. And this is something we are going to use in a strong way afterwards, right? So now the proof is going to be by induction. On the lexicographic order, on the couple, on MR, where this is the dimension of M, and R is the number of blowing up that we use in this sequence here. And yeah, induction on MR. And what was the comment that I wanted to make? In respect to the lexicographic order. So first, the kind of trivial trivial remark here, but which is going to be useful just to simplify things later on. Suppose that you start with X, which is contained. Suppose that X is contained into the exception divisor is 0. Then in this case, there's actually nothing to do in some sense. We can use the induction in a very simple way. So in the case that it's going to be contained in the exceptional divisor, recall that E0 is some union J from 1 to some S, where E0J are Q hypersurfaces. So now the result will follow in a simple way by the induction. So in particular, the dimension is smaller than the dimension of N. So it is enough to apply induction to E0J, X intersected with 0J for all J. So this is going to give us morphisms, let's call it F and J from N, J to M, such that Cj of Nj is equal to X intersected with this guy, and this is enough. And we conclude. We conclude easily because we can take as the manifold N the union, the disjoint union of all of the Nj's, and then the morph is phi, just as the morph is given by the restriction to each Nj, the Fg. So this is what the conclude easily means here. Okay, so I'm going to use this remark from time to time. Okay, so now the induction will start. The other trivial case of the induction is if M equals to 0, there's nothing to do. You just take the immersion going to be given by the set X into itself. X has to be either a point or empty. So it's not that there's nothing to do, it's just that it's trivial. The second thing is we have M0, then X must be contained already in the exceptional divisor. So this is because we are making no blowing up. So since we know that the preimage by the entire sequence of blowing up is contained into ER, so the only chance that we have is that it's already contained in E0. And we conclude by the remark. So now we can treat, and we need to treat separately the case MR and M1 separately. Sorry, we can just treat now the case MR directly since we started here. For R bigger than 0, right? I think because I had prepared with MR1, but probably I don't need it. Yeah, I don't need it right now. So if we now have some R which is bigger than 0, so now we have some extra points in the induction. So the first thing that we do is that we consider again, just as in the remark, the terms that are given here by the induction, given by E0J provided here. So we consider the morphisms Cj and J to M such that Cj of Nj is equal to X intersected with E0J as done in the remark. Moreover, there's another one that I want to use, which is the one given by the first blowing up. So we have a sequence of R blowings up, and I'm going to name the first one of them, sigma 1, will have center C1. So let C1 be the center of sigma 1. And we were going to also apply the induction argument for this guy. Consider C1 inter X. So C1 must be, note that the dimension of C1 is smaller than N, and apply induction. In order to obtain a morphism phi1 from N1, which satisfies all the properties that we want. It's semi-proper, it's generically immersive, all the properties that we want into N. And moreover, that this guy is equal to C1 inter X, which is again connected. And now we have to cover the other part of X. So we make the first blowing up. After the first blowing up, let I1 be the pullback of I0. The first I0, it was no zero there. Yeah. And X1 be equal to the zero locus of I1. And now we're going to apply induction. We apply induction. The couple M1 X1. So in this case, we do know that for M1 X1, so we made the first blowing up. And now here we're going to have the same dimension. M1 is going to have the same dimension of N because we just made a blowing up. And X1 will have a meta sequence of blowings up that principalize it, the ideal associated to it, by R minus 1 blowings up. So we can apply induction to it and obtain. Let me just write in the right notation. T tilde from N tilde to M1. So I recall semi-proper. Semi-proper. Generically immersive, duomorphism, all of the conditions that we wanted, such that phi of N tilde is equal to X1. Now this morphism here, it might not be good enough because we are going to, outside of the exceptional divisor E1, this is okay because there was no change in the set X. But X1 inside of the exceptional divisor might have components which are much bigger than the ones which are coming from X. Particularly, for example, it might contain a whole thing of the exceptional divisor, and then when we consider this phi tilde, when we consider the composition of phi tilde with the sigma 1, we're going to have something which is not in X, something which is too big. So we need to change a little bit this morphism. We need to choose a little bit these morphisms. Phi tilde in such a way that we're going to find the correct one, the one that is going to give us exactly X. X. This. And now there's another remark that we may use here, the following. So we consider N tilde equals to the union, this is always possible, where this alpha belongs to some index set where an alpha tilde is connected. Okay. Now, by lemma 2, we're going to have two options, either phi tilde, so I actually want to name it so that I can use it easier afterwards. Phi tilde of n tilde alpha is contained in the exceptional divisor E1. And here I'm using that E1 is locally given by a hypersurface. So there is a function there which defines the E1. So either this function, when I pull back by phi, is going to be constant equals to 0 in a connected open set by lemma 2, or it's not constant equals to 0. And therefore, by the lemma, there exists U alpha contained in an alpha, open and dense, such that phi tilde of U alpha, how did I write, is contained in x1 minus E1. It's a set where the E1 is the function that locally defines E1 is not equals to 0. So we're going to have this open dense set. And what we're going to do is simply take the indexes alpha where the second condition is satisfied, because the first one might create problems, and we had already covered everything that goes to E1 by the two morphisms that are here, these ones and the one that we did with the intersection of C1. So let's just choose a better index set. Let A be the alphas in alpha tilde, such that 2 holds. And now we just need to consider and let P2, oh, sorry, let me define everything that we need. N2 be the union by all alphas in A now of these n alpha tildes, and P2 from N2 to M, the composition sigma 1 composed with phi tilde restricted to N2. And now I claim that this is the, and now one needs to claim, one just needs to verify, it's enough to, we just need to verify. To verify that, in this case, phi2 of N2 is equal to x minus E0 union with C1 or bar, right? So if we verify this, then all of the other parts are going to follow almost immediately. Why? Because a blowing up is proper. So if we're composing a semi-proper with a proper morphism, it's still going to be semi-proper. The blowing up is a local isomorphism outside of the singular locus, outside of the center of blowing up. So in here, we have that this is going to be generically local immersion. In particular, it's going to be, we can even suppose that it's going to be a local immersion over the entire open dense set U alpha. And this part goes to something that it's not in the exceptional divisor. And therefore, the composition with sigma 1 is again going to be a local immersion. So it's enough to verify here. And this kind of follows in a not too difficult way because, so just little remark. that we know that.
Well, Andre, was it a part of your statement of the uniformization theorem that the morphism is generically immersive?
Yes.
Oh, sorry, I missed that.
Yes, because I want to define a dimension afterwards. Yes. Okay. So phi n tilde equals to x1, right? Which implies that phi tilde are then 2 must be given by x1 minus e1 bar, and then we obtain from this. And why is that? Because all of the other components are sent to e1, and of course we're covering phi tilde of n tilde was equal to the entire x1. So this is why this one is true. And from there, if we compose n2, this is going to be 2x. Can be verified then that this happens. Which is closed, and then here, this remark, which is closed. We are using that x is closed here to say that, well, we're not covering too much. This is what we needed to cover anyways. Okay. So this gives us the proof of this result, and now I wanted to say a couple of consequences of it, which are somehow useful to keep in mind. So the first one is that we may define now the dimension. We may define a dimension of x as a dimension of n. So that's why I asked the morphs to be a locally immersion, generically an immersion, so that because we haven't talked about the dimension of x yet. And with this, we can actually talk about the dimension of, like, dimension of n is going to be of a manifold, so it's well defined. And since it's a local immersion, it's going to make sense to call the dimension of x as the dimension of n. This is going to be compatible with the Hausdorff dimension of x. In the analytic case, just to make the remark, in the analytic case, we don't need the uniformization theorem to define this. The typical way, or the way that I learned from an article of Bierstein and Millman in the HS is from 88, is by using what is called separating families. But separating families do need Weierstrass preparation. The existence of what is called separating families depend on the Weierstrass preparation. So here I followed a different path, which is the one that is indicated in also the paper of Bierstein and Millman from both for Benjamin Carlin class for quasianalytic classes, where they do say that the result will follow that the dimension can be defined via the uniformization theorem. Indeed, we can do this. The other comment is that the proof that I have here is slightly different from the proof from where I learned from Bierstein and Millman's paper about the uniformization of analytic. But the idea is exactly the same. The idea is exactly the same. The only difference is that Bierstein and Millman use local resolution of singularities instead of global resolution of singularities, so they don't have this nice sequence of lines up, has just local sequence of lines up. And this means that the combinatorics is more complicated. But they do that because, at least at the time, resolution of singularities was considered a difficult problem, a difficult technique. And by now, the situation has quite radically changed. So I feel like we understand resolution of singularities very well. Bierstein and Millman helped a lot in this understanding. We have books about it. So I feel like we can use the result itself and have a less combinatorial, like a less hard from combinatorial perspective proof. Another thing is that in the proof, it's used the dimension of x, the induction is in the dimension of x2, and here I had to modify it in order to have this dimension of m of the ambient space. So it's a slight difference, but the idea of the proof is going to be exactly the same. The second consequence that I want to talk about is for what is called the topological noetherianity. So there's a theorem here. Maybe I'm going to put in the next part so that the theorem is in. So the true is a theorem which is called topological noetherianity quite a useful theorem. So let's take x1 a sequence of, and I'm going to use here the expression privileged Q sets of M, and a Q set of M just means that there exists a privileged ideal sheaf whose zero locus is equal to it. I'm just given here. I'm using this kind of in an abuse because I didn't define it before, but that's what it means. It just means that there exists an ideal sheaf, a privileged ideal sheaf whose zero locus is equal to the set. And then for every K, there exists K0 such that xk0 inter K is equal to xn inter K for all n bigger or equal to K0. So at some moment, even if the ideals are not coherent, at least from the point of view of sets, we know that we stop at some point. And just to give the sketch of the proof without doing the details, it's going to be an induction. So we may as well, so by lemma 2 again, we know that, well, not actually by lemma 2 yet. Let me do this correctly. We may suppose that x1 is not M, and by lemma 2, we know that the dimension of x1 has to be smaller than M, right? By lemma 2 and the uniformization theorem, we know that it has a well-defined dimension, and it has to be smaller than M, just by the result that we just seen, right? The Hausdorff dimension has to be at most the dimension of M minus 1, and lemma 2 says that essentially that it has to have then dimension D minus 1 at most. Or dimension D, right? If there was a part of dimension D, this would contradict lemma 2. So that's the point. And then we just use uniformization theorem. Phi from N to M, let me even call such that phi of N1 is equal to M. Pull back. So we take L equals to phi minus 1 of K. It's compact because phi is proper. And we consider YK equals to phi minus 1 of XK for all K. It's again privileged because you can just pull back the ideal sheaf, apply induction. Induction on the dimension. Since the dimension of N is smaller than the dimension of N. And somehow as a consequence of this too, we even have something nice, at least for presentation, that Q, that's ZX, be a Q set A in X. Then there exists an open neighborhood, U of A, and a function in Q of U, such that X inter U is simply the zero locus of F. And here I'm going to leave it as an exercise. It's really not complicated, but there's something to prove because the index, the generators of the ideal that is going to give us X locally, it doesn't have to, well, at least we don't know if it's countable. So there's something to adjust, but it's really not very complicated. Oh, and the fact that there's only one function is simply because if you are real and you find a finite number of functions, you just take the square and you sum all of them. And you just get one function in the end, whose zero log is going to give you the set, right? Here maybe. There's nothing correct with it. And now in the last 10 minutes, the only thing that I don't want to show to prove anything, I just want to state the result for the more general case. So this result that we did for uniformization theorem, oops, okay, recall, was for closed Q sets. So that's something that we had already seen. And I just want to state it for the more general case of sub Q sets. So I need to give you the definition of it, and then maybe say a couple of words about how to prove it. What is necessary for you to prove it. Okay. So let's start with a couple of definitions. The first one, X in M is a Q semi-analytic set if for every point A in X, there exists a neighborhood U of A and Fi in Q of U, Gij in Q of U. Oops. 1 smaller or equal to I and J smaller or equal to some D, such that X inter U is nothing but the union from 1 E equals to 1 to D of the set Fi equals to 0 and Gij bigger than 0. So this is going to be Q semi-analytic, exactly like the case of analytic. And now we even have an explanation of why we just need one function, right? And we're going to tell us that. And we don't have time. I'm not gonna give any example. I'm just gonna pass directly to the case of what is sub-quasianalytic. We keep this definition in mind. And then we're going to say that X contained in M is Q sub-quasianalytic if for every A there exists a neighborhood U of A. How did I present this? I'm presenting this one. And Y containing U times RK for some K a Q semi-analytic set. Such that if we denote by pi the projection, then P of Y is equal to X, and P restricted to Y is proper. And then in this context, it's still possible to prove the uniformization theorem. So the uniformization theorem here reads that X be a closed Q subanalytic set there exists a proper generically immersive Q map. I don't understand why I'm workshop map phi from M to M such that P of N is equal to X. Yeah. So this is the strongest version of the uniformization theorem that talks about quasianalytic. Now, in the last part, the last thing that I want to comment about is first one comment about the proof. The proof goes by basically three kinds of arguments. The first is the uniformization form, of course. Q set. A remark on semi-analytic. So the following remark is the set, sorry, let me write like this. F of X bigger or equal to 0 contained in Rn is the projection of y f of x minus y squared equals to 0 in Rn plus 1. So for a semi-analytic, you're going to be able to pass, apart from making a projection, at least if it's closed, to an analytic, to a Q set. And the third thing, the first point, is what is called the fiber cutting. Now, my point, I wanted, since I don't have time, I'm not going to state it. I wanted to state it, but I was actually not going to use it at any point in the rest of the course. I just wanted to say that it's a useful result and why it is a useful result. And the idea here is that if we look at the definition, we're not saying anything about the dimension of y compared about the dimension of x. And the fiber cutting lemma is what is going to allow us to have a relationship between this. It is essentially going to say that we're able to, given some projection from a y to an x, y q semi quasianalytic, then for each one of the points, the dimension of the fiber might be big, right? So you might, for example, in here have something of dimension 1, which is the projection, but the y itself had dimension 2, right? So there's nothing about the dimensions comparing y with x here. So the fiber cutting lemma essentially is going to be the technical result that says that you are allowed to choose in a nice way some other Q set here, or semi-Q set, yeah, B Q semi-analytic, but of the right dimension. Of the right dimension, if you look, like, we haven't proved yet the uniformization theorem to define what the dimension of f, but there's a way to, just as I did with the uniformization theorem, there's a way to talk about it without actually defining the dimension. This is just the heuristic about it, right? Just a technical result about this. And this is it's a quite useful result in combination with resolution of singularities. I'm going to talk a little bit more about it the next time. I'm going to make a little comment about column express with proof, but really just a comment. I just want to make a comment about it. And just, I want to finish with some sort of exercise example, which is a classic example of a subanalytic set, which is not analytic, which comes from Osgood. So let me just write Osgood. consider phi R2 in R3 given by phi of uv equals to u, uv, uv exponential of v. Show that phi of the unit ball is subanalytic but not semi-analytic. Okay, this is the classical example of Osgood. So I'm finishing now. So thanks a lot for everyone. I'll stop now. You can close the recording.
Thank you.
Thank you, Andrea.
Thank you.